Hi all, today we start discussing module 3. In this module we have three chapters, 9, 10 and 11. The ninth chapter is the Weingarten map. In this chapter we will discuss the local behavior of the curvature of an end surface. Our ultimate aim was to study how an end surface curves around in Rn plus 1 and how to measure the curvature of that. In this chapter, we will discuss we will study the curvature of a surface using the rate of change of the normal direction. So, we have already discussed how to define a normal surface. Unit normal vector field on a surface, then we will find out the derivative of that normal vector field. So in order to discuss the normal vector field, we need to be able to differentiate vector fields on n surface. So our first intention is to describe the derivative of a normal vector field or any arbitrary vector field. So for that we recall that for a given smooth function f defined on an open subset U which is in Rn plus 1, it is a function from U to R. First of all, we define the normal, we define the rate of change of this function. Now, if we have a vector V is in the set of all vectors about P, so this is plus 1 and P belongs to U. Okay, then the derivative of f with respect to V is defined as this f of f composition alpha derivative of this at the point t naught. Okay, so this t naught, this alpha of t naught using this alpha is from I to U for any parameterized curve alpha from I to U with alpha of t naught is equal to P. If this is the case, when we define then we define the derivative of f along the direction of V is f composition alpha derivative. This is d by dt of f composition alpha at the point t naught, and this is defined to be the del Vf. Okay, so this defines the derivative of this f. Okay, along the direction of V, and this is nothing but this d by dt of f composition alpha at the point t is equal to t naught. We know that since this alpha is a function from I to U and f is a function from U to R, then f composition alpha obviously a function from the domain of alpha to the codomain of f or the range of f. So that is what nothing but R. So this f composition alpha is a usual function from an open interval to R. Now this denotes the derivative of f composition alpha is the usual derivative of f composition alpha. But if we use the chain rule here, the behavior of this function is first we define this, if this is U and alpha, this f is from U to R, then this will be our f and this is our R, and we have alpha is from, suppose this is the domain of alpha, say I, this is alpha, and if you choose any t here, then that alpha of t is always an element of R plus 1. In fact, that is an element of U. So this alpha should have n plus 1 components, that is alpha 1, alpha 2, etc., alpha n plus 1. So this t is mapped to this alpha 1 of t, alpha 2 of t, etc., alpha n plus 1 of t. And f is applied on this n plus 1 tuple, and that is an element of this. So in order to use the chain rule, we have already discussed in the lemma in chapter 2 or 3, we can write this using the chain rule. We can write this derivative of composition alpha as del f of alpha of t naught dot this del f of alpha of t naught dot alpha dot t naught. So this is the this derivative, but we know that del f alpha of t naught is p. So this is del f of p dot v, because alpha dot t naught is equal to v. Okay, so if this is the case, we can say that if we choose any alpha with the property that alpha of t naught is equal to p and alpha dot T naught is equal to V, we can get this del F, del Vf is, del Vf depends only on the point P and V, that means that is independent of any choice of this alpha. Okay. That means in order to define the derivative of f along V, we choose a parameterized curve alpha with the property that you can choose any arbitrary parameterized curve alpha from this I to U such that alpha of T naught is equal to P and alpha dot T naught is equal. In this case, del Vf can be defined in this manner, or this value is, the final value will be independent of that alpha. That is nothing but del F of P dot V. Okay, this shows that del Vf depends only on P and V and F, P, V and F, and it does not depend on the choice of the parameterized curve alpha to evaluate this. Okay, so first you define this derivative of f is called the directional derivative of f along V. Okay, so this is the derivative f in the direction of V. So first we define this, then you can say that the directional derivative can be defined for every function u to r. Okay, and if you have a vector field x, then x of t is defined to be at the point P, or x of P is defined to be a vector at P. Okay, that is, this is x1 of P, etc., x n of P, n plus 1 of P, and if we have alpha such that alpha of T naught is equal to P and alpha is a function from I to U, and this x is defined on U to R, U to Rpn plus 1, Rpn plus 1, or any arbitrary vector field, then you can say that the derivative of this x along the direction of V, okay, the derivative of x dash of this along the direction of some V, we can define the derivative of this, and we use this the derivative as del V x rather than del V x, del V x rather than this x dash or x prime, and this is defined to be the vector at P. We define this as a del V x1, etc., del V xn plus 1. Okay, that is because these are all defined in this manner, because this x1, x2, etc. components are function from U to R. Then this x of P constitute this function, and the derivative of the directional derivative of this vector field along a vector V is defined to be the corresponding the vector whose components are the corresponding derivative of each of these components along V, or directional derivative of xi along V. So this is the way we define the directional derivative of a vector field. So now we are equipped with the derivative of a vector field, and using this vector field we will define the derivative of a normal vector field, and that quantity can be defined as the curvature or local curvature, or that can be considered as a measure of the rate of change of that normal vector field as the measure of the curviness in Rn plus 1, or the curviness of surface in Rn plus 1. Before we going to define the derivative of normal vector field, we list some properties of this this directional derivative of a vector field. That is, we have three interesting properties. Del V of x, the two vector field x plus y corresponding to x and y. This will be these are the consequence of the definition. Del V x plus this is del V y. Second property is this is del V of f, the vector field x, is same as del V f times this times x of p plus this f of p times This is analogous to the derivative of the product, del Vx. Del Vx. You can easily prove these things using the usual derivatives of the functions. And the third one, the last one is del V of x dot y. This x and y are two vector fields. Then this will be equal to del V x dot y of p, is y of p, plus this is x of p dot del V of y. So these are the three properties. Before we going to discuss the derivative of normal vector field, you can verify all these things using usual formula for usual derivative. So please do it as an exercise. So this is an exercise. Prove these three properties.